Clausius-Clapeyron equation. If the temperature of a two-phase system is changed, how does the pressure change? We have over here a system in a rigid container which is partially filled with liquid and partially with vapor. The system is at equilibrium and it is at a saturation pressure P1 and a saturation temperature T1. Now we heat the system. Some of the liquid evaporates and it becomes vapor. We have a new equilibrium where the temperature is T2 and the saturation pressure has now increased to P2. We can represent this process on a PT diagram. We can mark state 1, which is at P1, T1, and we can mark state 2, which is at P2, T2. Both of these are equilibrium states. We could draw a line in between them, and this curve is the equilibrium curve. The equilibrium curve gives the saturation pressure corresponding to a given saturation temperature, so all states along this curve are equilibrium states. On this PT diagram, P1 and T1 represent an equilibrium state, state 1. P2, T2 also represent another equilibrium state, which is state 2. The difference in pressure between P2 and P1 is Tp. The difference in temperature between T2 and T1 is Tt. At state 1, since it's an equilibrium state, we know the chemical potential of the liquid and the vapor must be the same. So therefore Gf is equal to Gg. At state 2, the chemical potentials also must equal each other. So therefore Gf plus Tgf, which is the chemical potential of the liquid at state 2, must equal Gg plus Tgg. Combining these, we have that Tgf is equal to dGg. This equation means that the change in the chemical potential of the liquid when going from state 1 to state 2 must equal the change in chemical potential of the vapor. We can use the Gibbs-Duhem equation to calculate changes in chemical potential. The Gibbs-Duhem equation says that Tg is equal to Vtp minus Sdt. At equilibrium, we know that the change in the chemical potentials for the liquid and the vapor must be the same. So dGf is equal to dGg. And substituting the Gibbs-Duhem equation, it gives us that Vf dP minus Sf dt is equal to Vg dP minus Sg dt. Rearranging that equation, we get that dP by dt is equal to Sg minus Sf upon Vg minus Vf. Now dP by dt is the slope of the equilibrium curve. Integrating this, we can actually get the equilibrium curve. Sg minus Sf is the difference in entropy between the vapor and the liquid. And this is something that we don't know as yet how to calculate. We can use the Gibbs equation to calculate changes in entropy. The Gibbs equation is that TdS is equal to du plus PdV. Now we want to relate the change in entropy to the change in enthalpy, as we will see very soon that that is much easier to work with. So let us start with the definition of enthalpy, that H is equal to U plus PV. Differentiating this, we get that dH is equal to du plus PdV plus VdP. Rearranging, du plus PdV is equal to dH minus VdP. Now du plus PdV is the expression on the right-hand side of the Gibbs equation. So let us equate this to the Gibbs equation, and we get that TdS is equal to dH minus VdP. This has given us a relationship between the entropy change, ds, and the enthalpy change, dH. Now we want to calculate Sg minus Sf. This represents the change in entropy of a mass which goes from the liquid to the vapor in a mixture at equilibrium. The two phases that we are dealing with, therefore, are the liquid and the vapor. dP would therefore represent the difference in pressure between the vapor and the liquid. But we know that at equilibrium, the pressure is the same in the liquid and the vapor. So therefore, dP is equal to 0. We can cancel out that term, vdP, and we are left that ds is equal to dH upon T. Let us now integrate this equation. We integrate ds from Sf, which is the specific entropy of the liquid, to Sg, which is the specific entropy of the vapor. On the right-hand side, we integrate dH from Hf to Hg. The system that we are dealing with is a saturated vapor in contact with a saturated liquid. We assume that the system is at constant pressure and temperature, so it is shown as being in contact with a thermal reservoir and a pressure reservoir. The temperature is the same in the liquid and the vapor, so T is equal to a constant. We can therefore take it outside the integral. Integrating this now, we get that Sg minus Sf is equal to Hg minus Hf divided by T. Let us try and understand what we mean by Hg minus Hf. Hf is the specific enthalpy of the liquid. Now imagine that we have a small amount of heat, delta Q, added to the liquid. Some of the liquid evaporates and it goes into the vapor, where it has a specific enthalpy, Hg. Delta Q, therefore, is equal to the difference, Hg minus Hf. We can therefore write Sg minus Sf as being delta Q divided by T. Let us define the latent heat of vaporization. And this is the heat required to convert unit mass of saturated liquid to saturated vapor at constant pressure. We will define, therefore, HFG, which is the latent heat of vaporization, as being equal to Hg minus Hf. Let us go back to the equation that we had for the slope of the equilibrium curve, that dP by dt is equal to Sg minus Sf upon Vg minus Vf. Sg minus Sf, we have just shown, equals Hfg divided by T. Substituting that, we get an equation which is known as the Clapeyron equation. This says that dP by dt is equal to Hfg upon T times Vg minus Vf. This gives the slope of the equilibrium curve, and everything on the right-hand side now is known and easy to measure. The latent heat of vaporizations of different substances have been measured and tabulated. The specific volumes also have been measured. Now we can simplify this equation further if we assume that the vapor is an ideal gas, so that Vg is equal to RT upon P, and that the liquid specific volume is negligible compared to the vapor. So Vf is much less than Vg. And at most ordinary pressures, this is a pretty good assumption. Making these substitutions, we can now write an equation that dP by dt is equal to Hfg times P upon RT square. Remember, this only applies if we assume that the vapor is an ideal gas. If we bring all the terms in P on the left-hand side and on T on the right-hand side, we can integrate and get that the integral of dP upon P is equal to the integral of Hfg upon RT square dt. Let us assume that Hfg is a constant, and this is a fairly good assumption for most substances. Hfg does not change very much with temperature or pressure. In that case, ln of P is equal to minus Hfg upon RT plus C, which is a constant of integration. We can rearrange this equation to say that Psat is equal to C exponent of minus Hfg upon R Tsat. This is now the relationship between the saturation pressure and the saturation temperature. We can calculate C if we have one known state. So we can draw this equation, which is known as the Clausius-Clapeyron equation, and we can draw it on a PT diagram. This represents the equilibrium states now. On the right-hand side, we have the vapor phase. On the left-hand side of the curve, we have the liquid phase. All states along that curve are equilibrium states. So, if, for example, the substance is water that we are dealing with, at 1 atmosphere, we know that the saturation temperature is 100 degrees C. If we have at 1 atmosphere, we take that water to 105 degrees C, then it will be in the vapor region. If it's at 95 degrees C, we know that it will be in the liquid region. If we raise the pressure of the water to 1.67 atmospheres, the corresponding saturation temperature is going to be 115 degrees C. Now, when we were talking about the Clapeyron equation, we called the two phases in the system liquid and vapor. However, we did not make any assumptions which would actually restrict it to being valid for just these two phases. In fact, the Clapeyron equation is valid for any two phases. So, for example, we could apply it to a solid in equilibrium with a liquid. We will represent a solid by the subscript S. Writing the Clapeyron equation for a solid liquid system, we can say that dP by dt is equal to HSF divided by T times Vf minus Vs. HSF over here represents the enthalpy of fusion or latent heat of fusion, and that would be the difference in enthalpy of the solid and the liquid. So we can write the Clapeyron equation for a liquid-solid system. So Tp by dt is equal to HSF divided by T times Vf minus Vs. HSF is always greater than 0. You always have to add heat to a solid to melt it and turn it into a liquid. Now, for most substances, the density of the liquid, ρf, is less than the density of the solid, ρs. So if you put a solid inside its own liquid, it'll sink to the bottom. Now, the specific volume is equal to 1 upon ρ, which means that Vf would be greater than Vs, in which case Vf minus Vs is greater than 0. Now, for water, ρf is greater than ρs, and water is an unusual substance because ice will float in liquid water. Vf, therefore, is less than Vs, which means that Vf minus Vs is less than 0. So, if for most substances Vf minus Vs is greater than 0, that means that dP upon dt is greater than 0. If we draw the PT diagram, the equilibrium line for the solid and the liquid has a positive slope. For water, however, it is different because Vf minus Vs is less than 0. dP by dt is negative. The equilibrium line between the solid and the liquid on a PT diagram, therefore, has a negative slope. The negative slope of the equilibrium curve between ice and water has interesting consequences. So suppose we have some ice, which is at pressure P1 and temperature T1. And at this condition, it is in equilibrium with water. Now we increase the pressure on the ice to P2. The equilibrium temperature, Tm, is now going to decrease. So as the pressure is increased, the melting point decreases. However, if the ice is still at temperature T1, it is at a temperature which is higher than the melting point, so the ice will melt. So suppose we have an ice block which is at temperature T1. We take a thin wire and we weigh it down, so we get a high pressure right underneath the wire. The temperature of the ice block, T1, is now greater than the melting point underneath it, which is Tm. The ice will melt and the wire will start passing through it. Behind the wire, however, where the pressure is now lower, the ice will freeze again. The wire can therefore pass through the entire ice block, but the ice is never cut into two parts. We can also write the Clapeyron equation for solid-vapor equilibrium, where solid is in equilibrium with vapor. In that case, dP by dt is equal to hsg upon T Vg minus Vs, where hsg is the enthalpy of sublimation, or the latent heat of sublimation. We can draw the equilibrium curves for all three phases, liquid, solid, and vapor, on a single PT diagram. This region would then be the solid, this would be the liquid, and this would be the vapor. We can represent on this the phase transition across each one of these equilibrium curves. So going from solid to vapor is a process of sublimation, from solid to liquid is melting, and from liquid to vapor is evaporation. The point where all three curves meet is known as the triple point. And at the triple point, all three phases, liquid, solid, and vapor, are in equilibrium. For water, the triple point occurs at a pressure of 611.73 pascals and at a temperature of 0.01 degrees C. At this state, we can observe ice, steam, and water, all three in equilibrium. To summarize, the Clapeyron equation can be written for any two phases in equilibrium, and it gives us the slope of the equilibrium curve. The Clausius-Clapeyron equation is written for liquid-vapor equilibrium, assuming that the vapor is an ideal gas. The saturation pressure increases with saturation temperature.